Deep in the jungles of Central America, man has battled nature to build an engineering marvel. Its epic story continues to astonish us. Its dimensions defy imagination. Its price, thousands of lives. It's the crossroads of the world's economy. To protect it, America has gone to war. It's the superstructure called the Panama Canal. December 20th, 1989. Under cover of darkness, 20,000 American troops invade the tiny Central American nation of Panama. As gunfire shatters the stillness of the night, the invaders pursue their prey. General Manuel Noriega, Panama's ruthless dictator and a suspected drug trafficker.
We ask you to surrender. If you do not, we are prepared to level each and every building.
4 days later, Noriega surrenders. The United States declares victory. But America has not put 20,000 lives at risk simply to arrest one man. Noriega's iron grip on Panama threatened one of the world's most important superstructures. The Panama Canal. The canal was born of a fierce struggle between man and nature. A battle that began at the dawn of the 20th century, when America's greatest engineers took on the biggest challenge of their lives and astonished the world. From 1904 to 1914, 40,000 workers dug and blasted their way through some of the toughest terrain on planet Earth. They dug the deepest ditch, built the largest dam, poured the biggest concrete structures the world had ever seen. They gave their sweat and they gave their blood. Thousands gave their lives. The Panama Canal links the Atlantic and Pacific Oceans at the Isthmus of Panama. A mere 50 miles wide, narrowest point between North and South America. When a ship enters the canal from the Pacific Ocean, two sets of locks raise at 85 feet above the sea. At this elevation, the ship sails 9 miles through a man-made channel carved from the mountains of the Continental Divide. Then 23 more miles across the second largest man-made lake on Earth. As it nears the Atlantic, another set of locks lowers it to sea level. By sailing through the Panama Canal, a ship saves nearly 30 days, the time it takes to sail around the tip of South America. Yet 5 million years ago, there was no need for a Panama Canal. The Atlantic and Pacific Oceans freely flowed between North and South America. Then, about 2 million years ago, the ocean floor erupted. 50 miles of volcanic rock arose between the seas. The Isthmus of Panama was born. Eons later, men dreamed of reopening the ancient path between the oceans. Digging 50 miles seemed seductively easy. But in Panama, it wasn't.
The Isthmus of Panama was one of the most difficult sites to dig a canal in the world. It was geologically unstable. It had mountainsides that tended to slip. It was seismically active, and it still is. It has a huge, almost impenetrable jungle covering it, and enormously jumbled varieties of stone and terrain.
At the end of the 19th century, men learned just how formidable a foe the Isthmus of Panama could be. In 1881, France undertook the world's first attempt to dig a Panama Canal. Confidence was high, and with good reason. In charge was one of the greatest entrepreneurs of his age, Ferdinand de Lesseps. It was de Lesseps who, in 1869, had accomplished one of the most impressive engineering feats of all time, excavating the Suez Canal across Egypt, joining the Mediterranean with the Red Sea. But the Suez was a ditch dug to sea level. In the flat deserts of Egypt, sea level was a mere 50 feet below the ground. In mountainous Panama, it was 10 times deeper.
They moved mountains to build the Panama Canal, but they didn't have to remove the entire mountain. If you build a sea level canal, you would have literally had to have removed the entire mountain.
French engineers began digging in 1881. Some 8 years later, they had excavated only a few miles of earth. Giant French steam shovels littered Panama's swamps, rusting and abandoned. Yet in the end, it was not only massive mountains that defeated the French. Europe's finest engineers had also been vanquished by an almost invisible enemy. Today, we know that mosquitoes transmit malaria and yellow fever, deadly diseases which even today afflict millions of people. But in the 1880s, no one suspected that these tiny insects could kill. Ironically, the French worried more about ants.
In order to prevent ants from crawling up on the beds of the hospital patients, they placed each leg of each iron bedstead in a cup of water, and that's where the mosquitoes bred.
Panama's 8-month rainy season bred mosquitoes by the thousands. And by the thousands, the French began to die.
People were dying so fast from yellow fever and malaria that when they brought you into the French hospital, the stories are that many times the pine box, the coffin, was brought in before you actually died.
In just 8 years, 22,000 members of the French Canal Company died of disease. The horrific death toll was matched by financial hemorrhaging. Ferdinand de Lesseps poured $287 million into his canal project and went bankrupt. It was the greatest financial disaster of the 19th century. In 1903, the exhausted French gave up and sold their Panama excavations to a young nation which had just proven its engineering prowess by taming a continent. The United States had the hubris to believe that it could succeed where the French had failed. Many wondered if it could. But the Americans understood something the French had not. To dig its canal, America would begin not with shovels, but with test tubes. A doctor, not an engineer, would lead the way. U.S. Army physician Colonel William C. Gorgas arrived in Panama in 1904. Gorgas was a controversial figure. Many dismissed his unorthodox methods of controlling disease. But these methods had worked brilliantly in Cuba after the Spanish-American War. In Panama, Gorgas assembled his weapons: 3,000 garbage cans, 4,000 buckets, 1,000 brooms, 5,000 pounds of soap, and 120 tons of insecticide. He sent battalions of workers into the streets and the swamps and the jungles of Panama with orders to hit the mosquitoes wherever they lived. Draining puddles and other mosquito breeding grounds, Gorges's army sprayed thousands of gallons of oil across ponds and swamps, killing the insect's larvae. Fumigating entire towns again and again. The cleanup took a year and a half, but by Christmas 1906, yellow fever and malaria had been virtually eliminated. To this day, the Canal Zone remains the most disease-free strip of tropical landscape on Earth. William C. Gorges would only be the first of many brilliant men to tackle the challenge of building the Panama Canal. It would be a task that would test the limits of each man's considerable abilities. For even without mosquitoes, Panama remained a formidable geological challenge. To dig their canal, American engineers mounted the biggest and most expensive peacetime endeavor in history. Again and again, they confronted seemingly insurmountable difficulties, inventing new and ingenious ways to overcome them. In 1992, Panama Canal engineers began a massive 10-year excavation project. They will dig and blast 40 million cubic yards of earth, widening the canal channel so today's gigantic cargo vessels can pass one another in its narrowest parts. It's the latest chapter in an engineering saga which began at the dawn of the 20th century. When the Americans began their canal in 1904, engineers laid out an ambitious master plan that would take 10 years to complete. That plan called for building 3 gigantic sets of locks, one on the Atlantic and 2 on the Pacific. To supply the canal with its water, engineers would need to dam the Chagres, the largest river in central Panama. The lake created by the dam would make it unnecessary to dig a canal all the way across Panama, because ships could sail some 23 miles across the lake. But between the lake and the Pacific locks, Panama's rugged backbone would have to be tackled with shovel and pick. This was the Continental Divide, an unbroken chain of mountains stretching from the Rockies in North America to the Andes in the south. Here, the canal builders would face their first challenge: digging a ditch 9 miles long, 300 feet wide, and 350 feet deep. It would not be easy. The French had tried to pierce this formidable barrier and failed.
The problem was that you didn't have stable hillsides. They looked like rock, but they were so badly fissured and layered in this direction that they kept on slipping. Every time you'd cut something, it's like digging a foundation for a house in mud.
To battle the Continental Divide, America sent an unlikely champion. His name was John Stevens. Stevens had never built a canal. He was a railroad man, famous for laying track and blasting tunnels where no one else could. When he arrived in Panama in 1905, he was 52 years old and had built over 1,000 miles of railroad in the United States. As much as any man alive. But could a railroad man dig the world's toughest canal? John Stevens pondered the abandoned French excavations, a shallow ditch called the Culebra Cut. his railroader's mind grasped a crucial fact which the French hadn't. The key to conquering Culebra Cut wasn't excavation, it was transportation.
One of the biggest technological challenges in completing the Panama Canal was what today would probably be called construction management and systems engineering. How to move all of the millions of cubic feet of material that were being excavated, because you can't just dig dirt out, you've got to do something with it. And in order to do something with that magnitude of dirt, you have to have a rail system, a transportation system that is very sophisticated and very adaptable.
Under John Stevens, the 50-mile wide Isthmus of Panama was soon laced with over 450 miles of track, and trains moving dirt, men, and supplies with relentless efficiency. As dirt-laden flat cars raced away to dumping sites, a steady supply of empties arrived, ready for steam shovels to fill. But one difficulty remained: how to unload millions of cubic yards of earth. Finding no existing solutions, the Americans simply invented one. A 3-ton steel plow pulled by a powerful winch along the length of a dirt train. In 10 minutes, this ingenious device unloaded more earth than men with shovels could remove in hours. The railroad solved many problems, but it created another: how to move miles of railroad track to keep up with the advancing steam shovels. John Stevens invented a new device called the track shifter. This simple but effective machine allowed the railroad to follow the digging wherever it went.
What he did was design a crane that moved along the track itself, leaning forward and picking up the track in front of it, lifting it, and moving it a couple of feet to the side, then moving along that track and doing the same thing a little bit further on and on and on.
But John Stevens didn't stay to execute his brilliant plan of attack. As soon as he had organized the canal excavations, the headstrong railroader abruptly quit.
He basically said that the difficult work was in the organization and the design, and that the construction itself was no big deal. And once it became nothing more than just a big construction project, he went elsewhere. He went off to Russia to find new challenges.
Stevens' departure infuriated President Theodore Roosevelt. The president turned the job of digging the canal over to Army Colonel George W. Goethals. Said Roosevelt, "He can't quit unless I order him to." Second in his class at West Point, Goethals had distinguished himself in the Army Corps of Engineers. He would use his absolute authority to weld America's canal diggers into a perfectly disciplined human machine.
He immediately put the whole canal zone under martial law and therefore could decree what had to occur. He didn't have to convince. He didn't have to argue.
In 1908, Goethals decreed that the canal channel would be a full 50% wider than Stevens had planned it. Once again, men and machines assaulted the Culebra Cut. Leading the attack were 68 of the biggest earth-moving machines ever built. Giant 95-ton steam shovels made by the Milwaukee firm of Bucyrus. Each of these iron leviathans could scoop up 8 tons of dirt, more than 3 times the capacity of the steam shovels used by the French. The gigantic shovels dug day and night into the Continental Divide, filling a carload of dirt every few minutes. And day after day, the explosions never ceased. 400,000 pounds of dynamite and 800 blasts every month. Under George Goethals' relentless assault, Culebra Cut deepened to 350 feet, At the time, the largest excavation ever made in the surface of the Earth. Tourists flocked to Panama and stared in awe at the mighty work before them.
To people living at the time, building the Panama Canal was a sign of progress. It was a clear evidence of the advantages, the industrial advantages, the political advantages of the United States over all other countries. It was clear to them that we were opening up a newer, and a better world all the time, and that things could only get better and even larger.
But the Panamanian soil would not yield to progress without a bitter fight. Huge landslides engulfed equipment and mangled railroad track. In minutes, months of digging disappeared. Miraculously, landslides killed only a few of the 6,000 men working in the Culebra Cut. Dynamite was a different story. The blasting crews were mostly black laborers recruited from Caribbean islands. They did the most dangerous work of all. No one was sure how much dynamite was needed to blast the cut. Every explosion was a matter of trial and error. When there was an error, men paid with their lives. In the worst single accident, 23 men were killed when a massive dynamite charge went off prematurely. A worker from the West Indies recalled, "The flesh of men flew through the air like birds." The Culebra Cut took 9 years to complete, longer than any other phase of the canal's construction. But the battle between man and the isthmus continues to this day. Today's canal engineers have new weapons in their war against the ever-shifting Earth. Using satellites and global positioning systems, they track Earth movements with pinpoint precision. But predicting landslides is not the same as preventing them. Engineers doubt that their battle with Panama will ever end. Nature has thrown many obstacles in the canal's path. Culebra Cut was only the first. Conquering these challenges would make engineering history. When American engineers began digging in Panama, they had to decide whether to build a sea level or a lock canal. Because it gets its water from the ocean, a sea level canal must be as deep as sea level. But in the mountains of Panama, sea level is over 500 feet deep. So the Americans rejected the French idea of digging to sea level. They planned to use locks to raise ships 85 feet above the sea. But building a lock canal created a new problem to be solved. Engineers would have to design and build locks capable of raising ships 85 feet. No canal had ever lifted ships that high. In theory, the locks would need immensely powerful pumps to raise water and ships 85 feet against the force of gravity. But the canal builders had no intention of struggling against gravity. They decided to make gravity work for them.
The most brilliant aspect of the design of the locks are all the water that flows into them and out of them is basically gravity flow, which means that they don't need pumps.
To exploit the force of downward flowing water, canal engineers first had to capture it. In Panama, that was easier said than done. Since time immemorial, tropical downpours have soaked the Isthmus of Panama. Over 10 feet of rain can fall in a single year. Bloated by this immense rainfall, the Chagres River once roared unrestrained across central Panama, from the mountains to the sea, wreaking havoc with its devastating floods. Engineers knew that there could be no Panama Canal until they had tamed the Chagres. They calculated that to control the raging river, they would have to build an earthen dam 100 feet high and 1.5 miles wide, the largest dam of its time. It was a bold design and highly controversial. 17 years earlier, in 1889, one of America's largest earthen dams had collapsed after heavy rains. Moving with the force of Niagara Falls, a 40-foot wall of water swept through the nearby city of Johnstown, Pennsylvania. 2,000 people drowned. Johnstown was annihilated. Fearing another Johnstown, some Americans questioned the wisdom of building the world's largest earthen dam in a country plagued by torrential rains. But canal engineers insisted that their dam would hold. Begun in 1906, Gatun Dam was finished in 1913. Behind its massive wall, the Chagres spread out and drowned 164 square miles of jungle, creating Gatun Lake, at the time, the largest man-made lake in the world. 23 miles long, the lake provided nearly half the length of the canal and gave the locks the immense amount of water they needed to operate.
The Chagres River was really the lifeblood of the whole canal, and it still is today. It provides the water for the whole system, bringing it in at the summit of the canal and guiding it down through the locks until it flows into the oceans.
Because Gatun Lake is 85 feet above sea level, the force of gravity propels its water downhill toward the sea. But the canal's 3 sets of locks, Gatun locks on the Atlantic, Pedro Miguel and Miraflores on the Pacific, act like plugs in a gigantic bathtub, preventing the lake's trillions of gallons of water from reaching sea level. To raise and lower vessels, the lock operators need only to open and close a series of valves. Water seeking sea level flows into or out of the chambers, raising or lowering ships as it goes. It takes 26 million gallons of water to raise one ship, and another 26 million to lower it. Enough water to meet the needs of a large city for 2 days. To handle this enormous amount of water and accommodate the biggest ships afloat, canal engineers would design the largest concrete structures of their time, so massive that no one was sure they could be built. The Panama Canal's locks are so well designed that today's enormous ships can still travel safely through them with only inches to spare. Before any ship ventures into a lock, canal workers tether it to 4 electric locomotives called mules, which travel on either side of the lock on a high-voltage rail. As the ship moves through the lock, a canal pilot on board tells the mule drivers when to reel in or let out cable. Like fishermen playing an enormous marlin, the locomotives keep the ship from hitting the lock walls. It's a system that works as well today as it did in 1909, when canal engineers designed the lock chambers specifically to fit the two biggest ships in the world. One of those ships was the brand new battleship Pennsylvania, 97 feet wide and 600 feet long. The other was a British luxury liner in her first days of construction. When finished, she would be 883 feet long and 93 feet wide, the biggest passenger ship afloat. Although the locks were designed for her, she never sailed through the Panama Canal. Her name, RMS Titanic. To accommodate the Titanic, the lock chambers would have to be the largest concrete structures in history, each one 110 feet wide and 81 feet tall, higher than a 6-story building. Even today, if stood on its end, a single lock would be the 4th tallest structure on the Manhattan skyline, topped only by the Empire State and Chrysler buildings and the World Trade Center. Only when the locks are drained for repairs can we appreciate their awesome dimensions and understand why those who witnessed their construction compared them to great cathedrals. Never had concrete been poured on such a massive scale. No one was absolutely sure that it could.
The problem with casting concrete in massive amounts is that concrete is an exothermic material. In other words, it gives off heat as it hardens. So the hotter it gets, the more danger there is for the material to crack. And the more volume you have, the more dangerous it gets for things to crack too.
There were other problems. Engineers were unsure exactly what mixture of gravel, sand, and water made for the strongest concrete. If they poured it too late after mixing, it would set improperly. Most difficult of all, building with concrete meant every detail of the lock had to be pre-formed in huge wood and metal molds. The lock chambers would have to be cast like enormous concrete pottery. To succeed, the canal builders had to do something never done before: pour millions of cubic yards of concrete with absolute precision and perfect timing. It seemed impossible. But for the men who built the Panama Canal, impossible was not an option. Engineers stretched steel cable between giant movable towers. From the cable hung enormous buckets, each holding 6 tons of freshly mixed concrete. The towers traveled back and forth over the building site, pouring concrete as they went.
The cable cranes were made of 2 very large towers mounted on tracks that could travel along the axis of the Panama Canal. They transported the dirt away, they transported the concrete in. They were very flexible because they could move in 3 dimensions. They could move along the canal axis and across the canal at the same time.
In 2 years using this system, the canal builders poured 4.5 million cubic yards of concrete, a volume equal to building a solid wall 8 feet thick, 12 feet high, and nearly 300 miles long. Today, computers control concrete pouring, but we still build huge concrete structures with the techniques and equipment invented for the Panama Canal. The lock designers topped their concrete pouring triumph with yet another dazzling innovation. In the age of nuclear power, it's hard to imagine how electricity could have amazed our great-grandparents. But at the beginning of the 20th century, it was the cutting edge of energy technology.
Electricity was a brand new energy form. Edison had built the first electric generating plant in 1881, and this was just about 20 to 30 years after that. I don't think that electricity had been used on a building site in quite that extent before.
Unlike steam power, electricity was instant and precise. With the touch of a button, it turned on or off. In the blinking of an eye, it traveled through long wires to start compact motors that drove immense machines. Huge turbines turned by the force of the Chagres River powered 1,500 electric motors which ran the locks of the Panama Canal. An industrial world that ran on steam and animal muscle was deeply impressed. The Panama Canal showed what the new electric power could do. With concrete poured and electricity in place, only one challenge remained for the lock builders: the chamber gates. These gates had to be strong enough to hold back millions of gallons of water. To fit the world's largest lock chambers, they had to be the biggest lock gates ever built, as tall as 6-story buildings. To remain watertight, the gates needed to open and close with flawless precision. In short, they had to be engineering miracles. Massively strong, yet light as feathers. And they were. On dry land, each lock gate weighs 700 tons. In water, it floats. The buoyant hollow frame makes the gate lighter than water.
This is a very important feature of the design of the lock gates, because this means that the machinery that is necessary to open and close them doesn't have to move a very heavy, massive steel gate, but really only has to move something that is buoyant in the water.
Massive steel rods open and close each gate. Moving the rods are huge gear wheels, 20 feet in diameter. Yet incredibly, the whole system runs on a single 40-horsepower electric motor, no more powerful than a motorcycle engine. When the gates were finished, engineers tried opening and closing them in the dry lock chambers at their full weight. One observer noted that each 2 million pound gate swung as easily as an ordinary door. Gravity was the heart of the locks. Electricity was their nervous system. Engineers gave them a brain, the control board. Today, the original control boards built in 1913 still run the locks. Each board is a tabletop model of the entire lock operation. But unlike a real brain, it cannot make mistakes. As lock operators turn its valve handles, letting water in and out of chambers, opening and closing gates, the entire lock operation unfolds in miniature before their eyes. Everything must happen in correct sequence. Beneath the board, controls are ingeniously interconnected. No one can throw a switch or turn a valve out of order. If they do, the lock operation stops.
The lock system had a whole series of fail-safe devices. It was more like the organization of a military campaign, where each module fit exactly into another organizational module until the whole thing could work. If any piece were left out, if any step were left out, in the organization of how to open and shut these gates, how to move ships through the canal, it wouldn't work. It would shut down.
After 4 years of construction, the locks were finished. By then, the Panama Canal was finally nearing completion. In May 1913, 2 steam shovels met nose to nose in Culebra Cut and excavated the last few buckets of soil. The canal was finished. All it needed was water. On October 10th in Washington, D.C., President Woodrow Wilson pressed a button, setting off an explosion 3,000 miles away in Panama. Hundreds of dynamite charges blew the final yards of Earth sky high. Water from Gatun Lake rushed into the Culebra Cut. But the Panama Canal had been dug as much for strategic military purposes as for commercial shipping reasons. Once finished, it would become one of America's key military assets and one of its most vulnerable targets. On August 15, 1914, the USS Ancon was the first ship to pass through the Panama Canal. A dream hundreds of years old had come to pass. 6 months ahead of schedule and 4% under budget. But it was a dream with a staggering price. In 10 years, the United States spent $352 million to build the Panama Canal, 5 times more than America had spent on the Louisiana Purchase and all other territorial acquisitions combined. The cost in human lives was no less cheap. More than 5,000 American deaths, nearly 25,000 French. 500 lives lost for every mile. The canal builders had carried out one of history's greatest construction projects and could only wonder if their accomplishment would stand the test of time. They could not know that within 50 years, the Panama Canal would face a deadly peril. At the end of World War II, the crew of an American warship in the Pacific were astonished to see what appeared to be a prehistoric monster rising from the deep. In fact, it was a Japanese submarine, 400 feet long, the largest underwater vessel of its time.
The E-400 series submarines are something that the world has never seen since or even before. These were gigantic submarines. They had a displacement of 4,450 tons, which was almost twice the size of the largest American submarine. So this is quite an impressive machine.
Examining the subs, American sailors discovered a strange tube and a long metal track. The Japanese explained that the tube was actually an airplane hangar, ingeniously designed to hold seaplanes called Sirens. Like aeronautical origami, the Sirens literally folded into their tubular homes. Once on the surface, the subs would launch their planes by catapulting them off their decks. The top-secret aircraft had been designed to perform only one mission: destroy the Panama Canal. The attack plan called for a fleet of 18 giant subs to launch 10 Siron seaplanes off the Panamanian coast. The planes' bombs and torpedoes would hit the canal's weakest points, Gatun Dam and the lock gates. With its dam and gates destroyed, the canal would have drained like an unplugged bathtub, crippling America's ability to move men and ships between two theaters of war. But in the early days of the war, aware of the canal's vulnerability, the U.S. military put into action a secret plan of its own. "100 feet under the locks, a maze of tunnels led to Special Items Project 7, SIP-7 for short. SIP-7 was two enormous hydraulic jacks, each weighing 100 tons, supporting a massive slab of steel hidden underground. This film offers a rare glimpse of SIP-7 in action. Pushed upward by the underground jacks, the huge steel dam rises in a lock, capable of holding back trillions of gallons of water if bombs ever shattered the lock gates. World War II ended before Japan could launch its attack against the Panama Canal. Instead, its giant subs ended up as target practice for the U.S. Navy. Today, the National Air and Space Museum in Washington, D.C. is restoring the last of the Panama Canal bombers.
The Ciron aircraft are the only submarine-based airplanes ever designed and put in operation that were intended as an offensive weapon. The Ciron that we have here in this museum is the only clue left in the world of this weapon system. And we're very proud to have this because of the threat that it did show against the Panama Canal and what could have been done.
At the close of the 20th century, much has changed at the Panama Canal. The technology of the future works side by side with the innovations of the past.
Okay, Captain, what's the ship doing? He's gonna hit us. Oh, nothing we can do here, Captain. We'll do it.
Veteran canal pilots use state-of-the-art computer simulations to teach trainees how to avoid catastrophe.
It's very important because you have to keep in mind the hydrodynamic effects, the interaction between the two ships.
Today, the biggest ships using the canal are called Panamax vessels. Panamax ships are over 950 feet long and over 100 feet wide. The lock chambers are 1,000 feet long and 110 feet wide. There's literally no room for error.
You do a good job entering the locks, and you can see the face of the master right away with a big smile. And if you don't, then you see him looking the other way, and that's perhaps your biggest punishment.
The world is changing too, beyond anything the canal builders could have imagined. The largest of today's supertankers and aircraft carriers are too big for the locks. There's talk of building high-speed railroads across Central America to compete with the canal. But as the year 2000 approaches and the canal passes from American to Panamanian ownership, this superstructure that once astonished the world continues to serve it well. Since the canal opened in 1914, nearly 800,000 ships have passed through it, carrying over 5 billion tons of cargo. Oil, wheat, computers, automobiles, and vacationers flow perpetually through its 50-mile channel. 15,000 ships a year, 24 hours a day, 7 days a week, 365 days a year. As the 20th century ends, no one expects the Panama Canal to fade into history.
God, I tell you, I admire those people who build this thing. Sometimes you go through the canal and you're concentrated on the job and you don't think about it. But then once in a while, you have a passenger, for example, on a ship that asks you something about the canal. And then you start talking about it, and then you look at one of the hills and then you feel this incredible admiration for these people.
Here, nearly 100 years ago, human beings took on one of nature's greatest challenges and won. Whatever its future holds, the Panama Canal will always be a monument to that victory. It will forever commemorate the genius, spirit, and raw determination which triumphed so decisively over such incredible odds. They seem to defy gravity. Forged from concrete and steel, skyscrapers loom over today's urban jungle. They embody the souls of those who built them, the strength and courage of high steel workers, but also the danger of such a passion. For as gracefully as they rise, skyscrapers collapse with unparalleled devastation. Yet in the face of potential disaster, architects continue to design these superstructures higher and higher. It's become a race towards the heavens to lay claim to the title, tallest building in the world. How far and how high will this never-ending race take us? And what engineering marvels keep these superstructures standing? In Nagoya, Japan, despite continual rainstorms, work progresses on one of the world's largest skyscrapers. The JR Central Towers, still in its infancy, is being built in the middle of a crowded city and on top of a busy train station. Every facet of modern engineering skill is daily put to the test. When completed, this enormous skyscraper will encompass over 4.5 million square feet.
It's about the size of the Pentagon, or larger than one tower of the World Trade Towers, the Twin Towers, and one of the largest buildings in Japan, if not the world.
Engineers in Nagoya, like many throughout Japan, have no choice but to build up. Land is scarce, and real estate prices are soaring. To meet the needs of a growing population, skyscrapers are the only answer. In the capital of Malaysia, space isn't an issue. Land for construction abounds. Yet in Kuala Lumpur, a modern 1,400-foot skyscraper is being built. The Petronas Towers are an amazing structure of glass and steel. With 88 floors and 100-foot spires, these twin towers are a monument to architect Cesar Pali's dreams. Whether built out of need or inspiration, constructing these mammoth skyscrapers relies heavily upon technological advances. But modern science isn't perfect, and tragedy follows when one comes tumbling down. Unwavering before such catastrophes, engineers continue to build bigger and taller superstructures.
Well, I think man has always wanted to get higher and higher. He always climbed the mountain to see beyond. It's also getting up to be taller, to overlook everyone else, or to be recognized or to feel more powerful.
To build these modern-day monoliths, architects and engineers first had to conquer the force of gravity. During the mid-1800s, the only means of vertical transportation, other than climbing stairs, was a rope and pulley system driven by a steam engine. However, the system was too dangerous for passengers since the ropes often broke. Frustrated, Elisha Otis invented a safety brake that locks the platform to its guides. In 1852, what seems a minor invention paves the way for the modern elevator. Slowly, the public begins to trust the Otis elevator. Upper-level floors become fashionable and profitable as architects quickly adopt this new means of vertical transportation. Even with the use of an elevator, buildings rising above 200 feet remain a dream. The building materials of the day, bricks, stones, and mortar, are simply too heavy to allow great heights. But in 1885, with the invention of the steel cage structure, the modern skyscraper is born.
Rather than build up from the ground, they built a cage inside, your bone structure, your person, the skeleton, and then they put the skin on the outside. And then the weight of that material is held at each floor level rather than passed all the way down 5, 10, 20, 30 stories down to the ground and held at the bottom floor. No, it's all hung off of this very strong structural cage, which is much lighter now because it's out of steel.
Because the steel structure bears the majority of the weight, the exterior, or skin of the building, can now be made of much lighter materials, such as glass and aluminum. The result is an explosion of buildings taller than anyone has ever seen.
The limits on masonry buildings were about 200 to 250 feet, which is equivalent to about 20 stories. With the advent of the separation of the two systems, the skeleton from the skin, we became capable of pushing higher and much higher, up to 50, 70, 80, or the Empire State Building type, up to 100.
For over 100 years, the steel cage structure has enabled engineers to build skyscrapers higher and higher. It's the backbone of every tall building's design, even the 800-foot JR Central Towers in Nagoya. The skyscraper is made up of 3 steel cages. One forms the base of the building, while 2 rise up within each tower. Without this technology, skyscrapers rising above 20 stories wouldn't be possible.
In Malaysia, over 26,000 tons of steel and 160,000 cubic meters of concrete have been used in the framing of the Twin Towers. These 88-story steel and concrete skeletons will help the Petronas Towers claim the title, tallest building in the world. Higher and higher they rise. But at what altitude do skyscrapers become too dangerous? Over 50 years ago, a deadly incident magnified these risks. In 1945, the tallest building in the world is New York's Empire State Building, rising an incredible 1,250 feet. Built in just over 13 months, its claim as the tallest skyscraper will last nearly 40 years. Perhaps this building's greatest achievement is not its long stay at the top, but its jarring reminder of the dangers of building so high.
The Empire State Building and all New York City were wrapped in fog as a B-25 Mitchell bomber trying to reach a nearby airport crashed into the tallest structure in the world.
Although the pilot and 13 others died, the building sustained little damage and was open for business 2 days later. Its ability to survive a collision with a World War II bomber seemed to validate modern engineering technology. Soon, a skyscraper building boom swept across the United States. "29 years later, the Sears Tower is built 1,454 feet above Chicago, becoming the tallest skyscraper in the world. While skyscraper construction within the United States has steadily declined since the early 1970s, the JR Central Towers and the Petronas Towers are at the forefront of a building boom along the Pacific Rim. The competition is as fierce as ever.
You built a skyscraper, they're taller and taller. Some of them make absolutely no economic sense, but they're being built nonetheless. It's just amazing the number of projects that are being done out there. They're being done strictly for ego. There's no other reason. And there's no economic reason for them to be built other than sheer ego.
As this construction craze of enormous skyscrapers spreads throughout the Pacific Rim, the engineering world is once again thrown into a battle to become the world's tallest building. The Petronas Towers are planned to top off at 1,476 feet, 22 feet taller than the Sears Tower.
These very, very tall buildings, much as the World Trade Towers in New York or Sears in Chicago, helped give the city a certain image. And they've become very important to that city's overall status, symbol, and image. The tall building represents catching up with the West, or maybe even going ahead in some cases. As more than just pure need.
Only time will tell if this architectural pursuit will prove deadly. In New York, to avoid future collisions, airplanes were simply rerouted. But the engineers of the JR Central Towers and the Petronas Towers are threatened by unavoidable forces. They're building skyscrapers in one of the most seismic active regions in the world, where the threat of a major earthquake is constant. Relying on the innovative designs that enabled the Sears Tower and the Empire State Building to reach such monumental heights won't help. They weren't designed with earthquakes in mind. How safe will these new structures be when a violent earthquake shakes their very foundations? As construction continues on the JR Central Towers, the Petronas Towers nears completion. Engineers of both buildings hope their state-of-the-art technology will pass the test. If it fails, these latest additions to the tallest buildings in the world could come tumbling down. Modern building design will be pushed to its limits when Mother Nature strikes. The construction of the JR Central Towers is a collaboration of the top engineering minds in both Japan and the United States. It's also one of the most hazardous projects in the world. Located directly below the site is Nagoya Station. 1.5 million people pass through here each day, disregarding the huge skyscraper being built above them. But what would happen if an earthquake hit such a densely populated area? It's happened before. September 19th, 1985. A killer earthquake registering 8.0 on the Richter scale rocks Mexico City.
Sigue temblando un poquitito, pero pues vamos a tomarlo con una gran tranquilidad. Vamos a esperar un segundo para poder hablar.
More than 10,000 people are killed. and over 100,000 are left homeless as the quake damages nearly 3,000 structures. 400 totally collapse. And for the city's towering skyscrapers, once a symbol of modern Mexico, this is the most devastating quake ever.
The ground was actually moving back and forth for a minute and a half or so, about like this. It just sort of a gentle motion back and forth. And certainly most buildings, if you were in them, you'd get a little seasick, but you wouldn't feel very much. It's not a very violent motion unless you happen to be a tall building.
During the 90 seconds of shaking in Mexico City, some skyscrapers swayed 6 feet, 3 times farther than what is considered safe. Neighboring buildings slammed into each other, causing major damage. 10 years later, a small office in the Japanese city of Kobe is tossed upside down. Just one of the many casualties in a town devastated by a 7.2 earthquake. Over 100,000 buildings are destroyed. Another 80,000 are severely damaged. And in downtown Kobe, home to most of the city's skyscrapers, 60% of the buildings sustain significant structural damage. Over 20% are completely destroyed. It's in this seismic environment the latest skyscraper building boom has erupted. Whether guided by sheer need or pure ego, architects are designing some of the tallest buildings in the world on some of the most unstable land. But the devastating failures in both Mexico City and Kobe have provided the building community with valuable insights. When the Earth moves beneath these monoliths, the skyscraper's center of gravity becomes offset. The top of the building tends to lag behind the base, putting more stress on the columns.
At the very least, the building could end up with a permanent bend in it, which would yield it an economic total loss, although the occupants may survive the situation. The worst case would be that it got so far out of vertical that it actually fell over, and that, of course, would be a catastrophic situation.
Using computers to simulate the shaking a building sustains during a major earthquake, researchers discovered that strengthening a skyscraper's foundation may prevent these structural failures. In Nagoya, Japan, only 140 miles from Kobe, the engineers of the JR Central Towers are putting this latest research to the test. 4 stories below the proposed lobby, a vast digging campaign is underway. In this subterranean cavern, architect Paul Katz hopes to build the strongest foundation ever constructed for a skyscraper. To anchor the building to the foundation, engineers drive 125-foot-high steel beams 60 feet into the bedrock. Eventually, these columns will be encased in steel reinforcement bars and concrete. This will become the base frame of the building and bear the majority of its weight.
You can see here the tremendous amount of reinforcement that is needed not only to carry the weight of the building, but this is where all the forces of the building come down. And in earthquakes, this is the part of the building that resists the lateral shaking that an earthquake will affect on a huge structure like this.
As an added precaution, engineers will then fill the entire cavern with over 1.5 million cubic feet of concrete, creating what is called a mat slab foundation.
Is what we're seeing in the excavation here is entirely going to be filled with concrete, 5.5 meters in height, which in a way the whole building then floats on and helps support the building from tilting and unifies the entire building.
For a mat slab foundation to work, steel piles must be anchored in solid bedrock. Once in place, they're locked together into a stronger structure by the cement slab poured around them. Finally, the steel structure of the skyscraper above ground is bolted to the foundation piles below. This becomes the skyscraper's skeleton, a single rigid structure anchored by a cement slab able to absorb most of an earthquake's lateral force. The mat slab foundation prevents the steel cage structure above ground from swaying too far during an earthquake. The taller the building, the larger the foundation necessary. Because of the limited space surrounding the skyscraper, the JR Central Tower's foundation is forced to be excavated in an underground cavern, while the Petronas Tower's foundation will spread out, covering over 1.5 acres. The building that will become the tallest skyscraper in the world requires one of the largest mat slab foundations ever constructed. Before a drop of concrete is poured, the bedrock at the proposed site of the twin giants becomes an issue of concern for architect Cesar Pelli.
You need to go down to bedrock, and you had to go very deep to start finding limestone. And the limestone that we found was like Swiss cheese.
This fissured limestone requires drilling the building's foundation piles extraordinarily deep, over 400 feet underground, or more than 6 times the depth needed to build the JR Central Towers. Once the foundation piles are in, over 70,000 tons of concrete are cast into the mat slab. Pouring round the clock, the work continues for 3 straight days.
This was the largest single pour of concrete ever done.
Timing and precision of the pour must be perfect. If one side of the foundation were to dry and settle before the entire job is completed, an uneven base would result. If the skyscraper were built on an uneven base, the building's weight distribution would be uneven. Out of balance, an earthquake could easily bring it tumbling down. But will these enormous mat slab foundations safeguard the buildings during a major earthquake? Or could they still topple to the ground, as in Mexico City and Kobe?
Eventually we'll see an earthquake in a major city that's a very large earthquake, and I think the bad news is that we could see some severe unanticipated damage and perhaps even collapse of some tall buildings.
The JR Central Towers, soon to be Japan's tallest building, is designed to withstand a magnitude 8.0 earthquake. Its engineers believe the skyscraper is safe, built to withstand the types of earthquakes that frequently strike the island nation. A similar faith in building design has guided engineers in Los Angeles for years. And on January 17, 1994, when a magnitude 6.8 earthquake strikes Southern California, their faith is shattered. In some areas, engineering fails and structures crumble. Amazingly, none of LA's skyscrapers collapsed. But an inspection of their inner steel cage frames reveals major damage in the welds connecting the vertical columns of many buildings to their horizontal beams.
The cracks did not only remain in the body of the weld that connected the two pieces. Once it started, it propagated. That crack had the effect like a zipper effect. It went right through the main body of the column element, and it ruptured the column horizontally.
Luckily, the Northridge quake was short, only 20 seconds. Laboratory tests showed that had the shaking lasted as long as either Mexico City or Kobe, these cracked beams would have ruptured completely, causing structural failure in many of these buildings. While Los Angeles struggles to repair its damaged skyscrapers, The sobering news has sent shockwaves throughout the engineering world. The steel cage structure, once thought safe, is now vulnerable during a strong earthquake.
Engineers of the JR Central Towers and the Petronas Towers must now implement the latest technology to keep their skyscrapers upright. To safeguard the millions of people who use Nagoya Station under the JR Central Towers. And to keep the Petronas Towers as the tallest building in the world. In the aftermath of the Northridge earthquake in Southern California, tall building engineers have answered a troubling question. After years of research, a possible solution exists for the stress-induced failures that many buildings sustain during earthquakes. Skyscrapers all over the world, including the JR Central Towers in Nagoya, now use what's known as dampers. These devices, installed within the diagonal trusses of the steel cage structure, reduce the building's shaking during a quake, much like shock absorbers in a car.
If you put a brace diagonally across it, as you deform the frame, that element would shorten and lengthen. And so if in that brace you actually put a damper, some sort of hydraulic valve, then it would absorb energy as it lengthened and shortened.
A skyscraper with dampers can absorb up to 3 times more energy produced by an earthquake than a building without them. The longer a quake lasts, the more effective a damper can be, absorbing more energy with each shock wave. Tall building engineers have been quick to adopt the damper technology. 14 have been installed within Petronas Twin Towers, and 6 are being installed in the JR Central Towers. While engineers in Nagoya and Kuala Lumpur incorporate technology to combat potentially destructive earthquakes, another, more immediate danger swirls above. The wind affects all skyscrapers. The taller a building rises, the stronger the wind it faces. Skyscraper design must take into account these turbulent forces. Towering over 1,400 feet above Chicago, the Sears Tower sustains daily gusts that can average 75 miles per hour.
The wind force, by and large, dominates these very tall buildings, dominates the design. It's more important than the weight of the building in the sense of just holding it up. It is the dominant force. The wind is what drives the design of very tall buildings.
When wind hits a building, it acts much like the sail of a boat. In order to withstand these blustery forces, a tall building must be flexible enough to bend and absorb some of the wind, while still remaining rigid enough not to topple over or even snap in half. The JR Central Towers provides a model of how this balance is achieved. The 3 inner steel cages provide flexibility, allowing the towers to sway up to 4.5 feet in strong winds, while the rigid central core of reinforced concrete adds the stability needed to prevent the tower from snapping in winds gusting up to 175 miles per hour. However, as skyscrapers are built higher and higher, they encounter stronger winds and are required to sway even farther to remain upright. Architects must now deal with a whole new design problem.
It's going to wobble like a tuning fork in order to maintain its structural integrity under those forces. So the question now is a more difficult one. It's not artistic, It's not properly scientific, it's judgmental, and it's about human comfort. It's about, on those top floors, how much vibration can people in offices tolerate and be comfortable with? At what point do we need someone at the elevator vestibule at the top handing out Dramamine?
If a swaying skyscraper can cause motion sickness in average high wind conditions, then the occupants of the Petronas Towers had better prepare for a wild ride.
Reaching nearly 1,500 feet, the Twin Towers are designed to withstand the devastating winds that strike the region.
These swirling gusts can reach over 90 miles per hour. Already, the world record height of these towers has pushed modern technology to its limits. Each tower needs to sway almost 3 feet just to prevent a structural collapse.
Yeah, it's a little bit small.
But architect Cesar Pelli has a vision that will compound this problem. A bridge between the two towers, a structure that Pelli feels will be symbolic of something larger than the towers themselves, the human spirit.
We proposed the bridge connecting the two towers in the 40th and 41st floors. And the bridge with its supports marks a gate also to the sky.
Pelli's architectural vision clashed with the tower's physical reality. If each tower must sway independently, how can it do so while attached to the bridge? The realization of this dream will stretch both Pelli's and the engineer's skills to their limits. It takes over 30 hours for construction crews to lift the sky bridge into position. But the real danger exists after the 900-ton passageway is locked in place. What would happen if the swirling winds hit the Twin Towers from different angles simultaneously, and they swayed in different directions? The answer is frighteningly simple. The bridge will snap apart, plummeting over 600 feet onto a crowded walkway below. To solve this unique design problem, engineers borrowed something from earthquake technology: dampers. Critical to the sky bridge's design are its 2 spherical support legs, 117 feet long and weighing 60 tons each.
In essence, these 2 legs are enormous dampers that will help absorb the vibrations created when both buildings sway.
To prevent these legs from snapping off when each tower sways in opposite directions, a torque reduction system is used. Instead of anchoring them to the bridge and towers directly, the support legs are attached to a rotating plate that can twist at least 45 degrees in any direction. The result? The damper legs absorb the torque and sway, while the bridge's interior support system remains unaffected. After the towers open, the bridge will serve not only as a passageway between the 2 towers, but also as an escape route in case of fires or emergencies. This combination of artistic design and engineering technology allows Pelli to realize his architectural dream.
When I face that space between the towers, I am in direct contact with the sky, with a higher world.
Pelli was able to implement his design for the Petronas Towers. Sometimes the forces that can upset plans come from the most unexpected places. In Japan, where cable television hasn't taken root, most television signals are broadcast through the air. The JR Central Towers, as they're being built today, are round. In the original plan, they were square. However, it became clear that a rectangular tower 800 feet in the air would block transmission signals from local TV stations. The result would be a phenomenon known as TV ghosting.
TV ghosting is a very common phenomenon. If you're looking at your television set and you get 2 images that blur your reception, that's called TV ghosting.
The architects of the JR Central Towers were surprised by this structural problem and forced to make a multi-million-dollar design change or suffer the wrath of thousands of television viewers.
Those curves, from an aesthetic point of view, they were very nice, but also from a technical point, what it does is it takes a direct wave and then diverts it.
For a building to divert a broadcast wave, the exterior can't contain any metal or reflective glass that would cause the wave to bounce back toward the transmission tower. So the exterior of the JR Central Towers had to be made of precast concrete and ceramic tile, a much heavier skin than the glass covering originally planned. This extra weight on the frame of the skyscraper made it even more necessary to place a massive mat slab foundation underneath the building. In the end, the architects and engineers for both the JR Central Towers and the Petronas Towers are able to fulfill their visions. The 800-foot JR Central Towers will become the tallest building in Japan, providing desperately needed office and retail space to a growing metropolis. And the Petronas Tower will win the title, tallest building in the world. But have these engineers, while building such enormous skyscrapers, prepared for every disaster? Or is it impossible for an architect to prepare for the insanity of man? Designed to survive the battering of high winds and the violent shaking of earthquakes, modern skyscrapers seem indestructible. But where Mother Nature might fail, man has succeeded. On February 26, 1993, a nightmare becomes a reality. The bombing of New York's World Trade Center ushers in a dark new reality. The threat of terrorism has finally come home. The blast kills 6 people, injures over 1,000, and causes millions of dollars worth of damage. But as enormous as the force of the explosion is, it doesn't bring down the towers or even cause severe damage to the structure of the building.
You must understand that the towers were designed for the impacting of the largest airplane of its time, the Intercontinental 707 aircraft, right into the building.
In designing the World Trade Towers to withstand a mid-air collision, engineers learned after the bombing that they had inadvertently built a fire trap.
Both towers actually behaved like giant chimneys, and they took this air that was in this basement created by this great explosion and sucked it up into the towers and raised it up through and tried to expel it at the top.
Somewhere among 110 stories, 50,000 people are stranded in complete darkness. When emergency systems fail, smoke fills the towers and people become desperate for air. They smash windows in a frantic search for a way out. Yet they're alive because the tower didn't collapse. The steel cage skeleton absorbed the force of the bomb and prevented its collapse by distributing the blast shock throughout the entire frame. However, the inner concrete reinforced columns, designed to give the towers their rigidity, became the vertical conduits for the deadly fire and smoke. Eventually, firefighters were able to release the trapped smoke by smashing windows on the lower floors and cutting air holes in the roof of the towers. During the ensuing investigation, engineers discovered the structural design of the World Trade Center can survive a bomb's blast, but the building's emergency fire and sprinkler systems can't. They were knocked offline, allowing the spread of the fire and smoke. Since the current steel cage structure is essential to building a skyscraper, architects can't change this design component. Yet disasters like the World Trade bombing and the MGM hotel fire of 1977 can turn skyscrapers into towering infernos. Engineers are now challenged with developing an advanced infrastructure to ensure that the air, water, and fire systems can function under extreme situations. Once again, as architects continue to design skyscrapers higher and higher, engineers struggle to invent new systems to support these record heights. For the engineers of the Petronas Towers, simply providing water to the entire building becomes their biggest obstacle. Over 600 pounds of pressure will be needed to pump water to the pinnacle of this skyscraper, nearly 1,500 feet into the sky. Simply attaching a faucet or sprinkler to such highly pressurized water would be like trying to drink from the end of a firefighter's hose. To solve this problem, engineers decide to pump water to the very top of the building and then let it cascade down to pumps located in the maintenance floors below, losing its pressure as it trickles down. At each floor, the water is then distributed throughout the tower. In order to achieve this, 3 entire floors within each tower are dedicated solely to maintenance systems. Located at the 7th, 43rd, and 81st floors, these control areas handle the water, air, and electrical distribution for the floors attached to their zone. If during a fire or explosion one of these maintenance floors is destroyed, the other 2 can operate independently to suppress any fire and ventilate any smoke. During the World Trade Center bombing, once the main control area was knocked offline by the blast, all emergency systems throughout the skyscraper were lost. The 3 independent control areas in the Petronas Towers are designed to avoid just such a fate. This decentralized plan provides a reliable means to a more comfortable environment for the tenants.
You take it for granted that you're cool, you're warm, there's lights on, the bathrooms work, and there's some very, very sophisticated systems in your building, particularly today.
These high-tech solutions to old problems have made possible the continued growth of modern skyscrapers. But this technology doesn't come cheap. In Nagoya, Japan, it will take 7 years to complete the JR Central Towers. And it's costing $1 million a day to build this skyscraper. But for all the money that's spent, it's the skill of the high steel worker that makes all skyscrapers possible. In Japan, the people who work on these tall buildings are some of the most talented and dedicated workers in the world. At the JR Central Towers, the project is viewed as a team job. Each morning, workers perform calisthenics together. A detailed briefing of precisely what work needs to be completed that day follows. The coordination between departments is so precise that the day's work is planned down to the minute.
The skill of the worker in Japan is at a very high level. They devote their lives to the construction industry.
This dedication has paid off for the JR Central Towers. Construction is on schedule and under budget, with workers completing an astonishing 3 floors per week. Elsewhere around the world, the completion of 1 floor per week is acceptable. But for the many workers on the high steel in Nagoya, being average is not acceptable, and their passion is spreading. Japanese engineers and workers often train crews building skyscrapers along the Pacific Rim. They came to Kuala Lumpur, and the results stand before all the world to see. Highly skilled workers, technological advances, the dreams of architects. These are the ingredients to build the modern skyscraper. It's guided engineers to build the JR Central Towers 800 feet above a crowded metropolis in the heart of earthquake country. And it's inspired Cesar Pelli to design and erect the tallest building in the world as a monument to a proud city. But in this race to reach new and unimaginable heights, how high is high enough? The drive to create the tallest skyscraper in the world has been a 100-year odyssey sweeping engineers and architects far beyond their initial dreams. This ambitious race has led Cesar Pelli and the engineers of the Petronas Towers to the forefront of modern building design.
The $800 million invested by their builders have made the Petronas Towers the tallest building in the world. Their 88 floors soar 1,483 feet into the air. Or is it? Engineers of the Sears Tower say their building still retains the title, since it has 110 floors to Petronas' 88. But Pelli's building includes an enormous spire that tops the building off 22 feet higher than the Chicago skyscraper. Sears Towers officials counter that if Petronas' spire is counted, then the antennas on their skyscraper should be counted too, which raise its height 231 feet taller than the Malaysian giant. Pelli argues that his spire is integral to the design of Petronas, and the Sears antenna are just that, antennas. But if the height to the tallest antenna is the standard, then isn't New York's World Trade Center the tallest building in the world at 1,758 feet? This debate will become more intense very soon, because in Shanghai, ground has broken on the Mori Towers project. When finished, it will loom over this ancient Chinese city at a height of 1,509 feet, taller than both Sears and Petronas. In Hong Kong, Manila, and Tokyo, the city skylines are punctuated with buildings under construction. Is this where the next Petronas will rise? The key to taller skyscrapers is once again the elevator.
We took a 145-story building, put all the elevators in it that were needed by all the people in 3 million square feet that were to occupy that building. The entire floor plate would be taken up by the elevator core, and there'd be no space to rent and make money on. So, hey, that wouldn't work, right?
Recently, the Otis Company announced its latest creation, which many believe will solve this dilemma. An elevator that can move horizontally as well as vertically. By providing access to more areas of a skyscraper with fewer elevators, valuable rental space is opened up. Once a building becomes economically viable to investors, how long will it take before a higher one is built? And how long before another technological advancement comes along that raises tall buildings to unheard of heights? In Metropolis, filmmaker Fritz Lang's prophesizing drama of 1928, even the sky isn't insurmountable. But is there a physical boundary beyond which science can never advance? Years ago, a mile-high building with atomic-powered elevators connecting over 528 floors was designed by American architect Frank Lloyd Wright. If built, a skyscraper this tall would stand over 5 times the height of today's tallest structures. 40 years ago, a mile-high building seemed a futuristic folly. But is it still? As technology continues to advance, engineers now say a mile-high building is possible. New, lighter building materials are the key. Already, ceramics are being used in the exterior walls of the JR Central Towers to lighten the total weight of the building and reduce the stress on the earthquake-sensitive foundation.
The future is going to be, you do not limit yourself to natural materials like steel or aluminum or masonry, where you compose materials and you create new properties out of hybrid materials, alloys or ceramics or plastics, carbon fibers, or mixes of all this.
Eventually, these new materials will give rise to skyscrapers taller than anyone has ever seen, surpassing both the JR Central Towers and the Petronas Towers, today's architectural marvels. These monoliths of the future may also be closer to Lang's vision of the future. Not just a tower of office space, but self-contained cities within a building.
Everything is in one building. You can have retail, you can have hotel, office, apartments, and you can have transportation, all in one single building. You can go to one location and get everything you want.
Since their earliest beginnings, skyscrapers have evoked unexplainable emotions in us, from pride to awe to fear. Have they evolved to become buildings that provide the space needed for a growing population, or just an exploitation of those needs? A justification to build what Cesar Pelli calls a gateway to the skies.
I do not know if it's innate in human beings or acquired culturally, but there is something magic and extraordinary, or a structure that grows from the ground and moves up and reaches the sky. When you are up on a building, you and the ground are one. Somehow you feel that through your body, through your feet, through the structure of the building, you are still rooted on the ground, but you are looking above all other buildings. And there is just something extraordinarily satisfying. I imagine the tallest oak in a forest or the tallest sequoia must feel the same thing.
Perhaps these monuments that we leave behind tell much of the human story itself. They speak with stunning eloquence of our ambition and our brilliance, but also of our frailty. As they puncture the skies above our urban landscape, skyscrapers also punch holes in our preconception of what's possible. What was impossible yesterday now stands before us.
Deep beneath the English Channel, one of the most ambitious engineering projects ever attempted is about to begin. Using Earth-eating robotic monsters, 13,000 workers are about to embark upon an epic quest to build the longest undersea railway tunnel in the world. This historic journey will push the limits of technology and human determination to the breaking point. Some workers will not survive. But the creation of the Eurotunnel is a story of triumph, one of this century's greatest superstructures. Ever since the Ice Age ripped them apart 10,000 years ago, a small finger of ocean, the English Channel, has been the only path between England and Europe. Throughout history, countless lives have been lost trying to cross this treacherous body of water. For centuries, amateur designers and skilled engineers alike have tried and failed to create a safe, permanent link.
The first channel tunnel design, if you can call it a design, was in 1802. But at that time, the technology was so limited that really it was science fiction.
But by the end of the 20th century, the line separating technology and science fiction is rapidly disappearing. It is now possible to create machines the size of large buildings, machines that can literally move mountains. Inside factories like these, engineers begin experimenting with space-age technologies to take humans into new and potentially dangerous territories. Soon, an age-old question is asked once more. Can a tunnel be created under the English Channel? But does England herself even want such a passageway? From the days of Camelot to the age of Churchill, the Channel's cold, choppy waters formed an imposing barrier between the monarchy and its enemies. Would-be conquerors from Napoleon to Hitler developed plans of how they could first defeat the English Channel and then England itself. Ironically, during World War II, Adolf Hitler developed a plan to dig a tunnel near the captured French town of Calais, site of the modern-day French Eurotunnel station. It was a threat the Allied forces took seriously.
Bomber pilots were requested to report any plumes of grey material in the channel, and they actually established soldiers along the coast here with listening devices trying to detect any sounds of tunneling.
But with the defeat of Germany in World War II, Europe entered a new era. The sounds of war were replaced by the sounds of commerce. By 1986, one-time rivals England and France decide the Channel has become an economic barrier, an obstacle that must be eliminated. To achieve this, the French and British governments dedicate themselves to the task of building a modern marvel, the world's most technologically advanced undersea tunnel. Engineers and business people alike dream of high-speed rail trains traveling beneath the English Channel, carrying the citizens of a united Europe into newfound economic opportunity. But before the first shovel of dirt is even dug, the project seems destined for failure.
This was a nightmare at the time. We had to decide on things which we didn't really know about. And one example, which I always quote, is, what diameter do you want for the tunnel? Now, you would think that this was something that had been decided before, but it hadn't. And the contractors kept pestering us, saying, what size tunnel do you want? And we said, well, listen, we just arrived. I don't know.
For as long as we can all remember, people have dreamed of a channel tunnel.
As this ad, seeking Eurotunnel investors, points out, the project was financed solely by private investment, with an original price tag of over $10 billion. This made it very different from other large engineering projects of this century, like New York City's Lincoln Tunnel, which was government-funded. Ultimately, Eurotunnel had to answer to its shareholders. But despite the private backing, there was much public opposition, especially on the British side. Some opponents were concerned about the environmental impact of the project, while others didn't want to surrender England's status as a proud island empire. The project's decision-making body, a consortium of 10 companies called Trans-Manche Limited, or TML, is undaunted. They plan a design of 3 parallel tube-like tunnels. When finished, these massive tunnels will form a railway loop between England and France. Engineers envision a system that will carry thousands of passengers and hundreds of tons of freight each day on this circular 30-minute trip. Of the 35 miles between the French terminal at Calais and the British terminal at Folkestone, 24 will be undersea. No other project has ever attempted to tunnel this far in such a hostile environment.
There are lots of problems, technical problems. How will a car move inside the tunnel? What kind of trucks can I transport? You know, all the variety of things.
As the project begins in late 1986, all of these questions remain. But before issues regarding the tunnel's operation can be addressed, the most daunting and obvious problem must first be solved. A machine that can chew through more than 30 miles of solid rock, hundreds of feet below the sea, doesn't exist. It will have to be created. Thousands of miles from the English Channel, on the outskirts of Seattle, Washington, a solution is being forged of iron and steel. Here at the Robbins Company, a firm specializing in heavy mining and tunneling equipment, the next breed of super machines is being created. In this colossal factory is a mechanical beast that dwarfs its creators. It's called a tunnel boring machine, or TBM. When finished, this giant snake-like earth mover will be over 800 feet long and weigh over 1,500 tons. Its rotating head, almost 50 feet in diameter, consists of hundreds of cutting edges made from tungsten carbide, one of the hardest materials known to man. These will be the teeth of this mechanical monster, the cutting force it will use to chew through the earth below the channel. Pushing the machine forward is a series of powerful hydraulic devices called rams, which will drive the cutting head through the rock. The millions of tons of excess rock it will dig up, called spoil, will be carried out on conveyor belts through the TBM service train attached to the cutting head. The challenge of carving tunnels through solid rock has always pushed the boundaries of our engineering and manufacturing skill. Even today, it requires a rare balance of brain and brawn. When large-scale projects like the Los Angeles aqueduct system were being created in the 1930s, tunneling technology was in its infancy. Today, the Robbins Company will replace blasts of dynamite with a computerized mechanical marvel of which the early pioneers could only dream. But the danger these modern miners face will also be unparalleled. At its deepest point, the tunnel will be 246 feet below the seabed. During construction, if their boring efforts create a crack in the tunnel or cause a leak, the force of the incoming water will be equivalent to over 7,000 tons of falling weight. Man and machine would be crushed in an instant. At the Robbins Company, frightening scenarios like these must be addressed. Project organizers selected the tunnel's route precisely because it goes through a layer of chalk called marl, which is well suited to their tunneling efforts. It is also the last remnants of the original land bridge that once connected England and France over 10,000 years ago. While this chalk is ideal for tunneling on the British side, the situation on the French side of the channel is far more treacherous. Here, the seabed is riddled with faults and fissures, conditions that could lead to the deadly accidents engineers must try to prevent. Of the 11 TBMs that will be created for this mission, the machine that will be used on the French side faces the most difficult job. Working at greater depths, in parts of the seabed that are far less stable than the British side, this undersea giant will have to withstand pressures twice as intense as any tunneling machine has ever experienced. So engineers decide to create a special TBM that is part boring machine, part submarine. When finished, it will be able to withstand the same amount of undersea pressure as a World War II sub. Finally, the technology behind the dream of reuniting the European continent seems to be in place. And while the project will ultimately link England and France, the massive construction process will be an international effort. Companies from Germany to Japan will add their technologies to the mix, making the Eurotunnel a truly global undertaking. While this international force rallies to overcome the physical obstacles of the channel, there are other challenges already mounting. Namely, the race to complete the tunnel on time and on budget. It is now December 1987. This is where the Eurotunnel begins. 2 huge shafts at Sangatte, France, and Shakespeare Cliff in England. Too enormous to be delivered to the site as complete machines, the first TBMs are lowered piece by piece into the darkness of the shafts 200 feet below. Going with them are the workers, the men behind the machines. They too are descending into the unknown, taking the first steps of an epic journey. As the first work begins and the light of day slowly disappears, there is an air of hope, expectation, and much uncertainty. While extraordinary safety measures have been taken to protect the workers, it remains a dangerous world. And for some, the greatest civil engineering project of the 20th century will carry the ultimate price tag. As giant mechanical earth eaters are given a final check before being lowered to their work site hundreds of feet below the ground, one of this century's most ambitious engineering projects is underway. The creation of an undersea railway that will link England and France begins here in Sangatte, France, and here at Britain's Shakespeare Cliff, near the site of the future Folkestone Terminal. What officials hope will someday be the world's premier railway system is now just a hole beneath the earth. The race is on. Compounding the awesome challenge of the actual tunneling operation is a human challenge. British and French workers, once bitter rivals, must now learn to work together. Once they reach the dark and dangerous caverns deep below the earth, there can be no room for cultural misunderstandings.
A French engineer is trained to make a plan. They can't start work unless they can see what there is to be done, see where their task fits into the whole thing, and see how it's all going to be organized as it goes along. No such thing in the British culture. British culture is to sit down and say, now what have we got to do, chaps? And sort out who's going to do what and set to work.
One of the first problems they face is the assembly of the giant tunnel boring machines, which the workers christen the moles. Even the smallest machine takes months to build and costs several millions of dollars. The largest of these subterranean titans weighs 1,500 tons. Because of their enormous size and weight, the TBMs must be assembled on site, which in this case is far below the earth. The actual cutting head of the TBM is just the tip of its immense body. Attached to it is the service train, a multi-car train system that carries the hydraulic power to drive the TBMs forward. When connected to the cutting head, each service train is a staggering 850 feet long. One of the service train's main functions is to be a conduit for the removal of millions of tons of rock and sediment these mechanical moles will dig up. The debris will be carried by conveyor belt through the service train to a supply train and back, and finally to disposal facilities in England and France. The removal of the spoil is a major challenge. When operating at full speed, engineers estimate the TBMs will cut through 750 feet of rock per day, removing 2,400 tons of waste per hour. When the project is finished, the total amount of rock removed would fill a major football stadium 13 times. But equally important as taking material out of the tunnel is the challenge of getting materials in. And one of the most crucial building blocks at this underground work site are the 500,000 concrete slabs which will line the tunnel walls. Because these concrete rings will provide a life-saving barrier between passengers and the churning English Channel above them, their construction is of utmost importance. Special factories are built in England and France to manufacture these vital sections. Each ring is made of specially reinforced concrete, even stronger than the concrete used in nuclear power plants. It is also reinforced with a framework of steel rods for extra resistance. This is necessary because the savage ocean pressure that will bear down on the tunnel walls is equivalent to 12 atmospheres, or 12 times the pressure we feel on the surface. No human could survive under such immense force. Once the rings are finished, they are transported by narrow gauge railway to the TBMs in the tunnel and brought up through the service train. Then, a remarkable display of mechanical symmetry takes place. As the spinning head of the machine claws its way through the rock, operators using giant cranes create the tunnel walls, right behind them. After being fitted into place with incredible precision, a gap of only 3/4 of an inch remains between each section. This tiny space is then sealed with a cement grout, and another piece of the tunnel wall is complete. When finished, each ring of the tunnel will weigh 40 tons. But just as the skeleton of the tunnel is beginning to take shape, the project suddenly seems in danger of falling apart. It is now 1988. The British and French teams are starting with the middle service tunnel, drilling towards each other to meet in the middle of the channel. But by May, the giant tunneling machines begin to break down.
It was designed to operate at pressures that no machine had ever operated before. It was strictly a prototype as a result of the fact that it was so complex and nothing like it had ever been built. It had all kinds of troubles. Practically everything important on the machine failed or broke at one time or another shortly after we installed the machine.
On the French side, the TBMs are encountering precisely the scenario engineers feared the most: hidden faults and fissures in the seabed. On the other side of these cracks lie the awesome forces of the English Channel.
It was technically very difficult because the water pressure that we had to work in, as the machine bored forward, it bored right through faults that were filled with seawater, connected directly to the ocean.
Waterproofing measures designed to protect the TBM's delicate electronic equipment from the seawater fail, stopping the giant machine in its tracks. Then, as engineers scramble to repair the electrical problem, another even larger problem develops.
This is the seal we intend to use. It's a wire brush type seal.
The ring of watertight seals providing a life-saving barrier between the TBM and the tunnel walls also begin to fail. Again, victims of saltwater corrosion. Engineers need a solution, and fast. The corroded brush-like lining seals are replaced. Then, a mixture of paper and special grease is applied to the brushes. When this coating comes in contact with seawater, the paper particles expand and create a permanent, watertight bond between the segments. The TBM is once again waterproof. But to Robbins Company President Richard Robbins, the tunnel walls seem far more secure than the legal agreement he is working under. Soon he is forced into a desperate personal gamble.
The French contractor knew that we had designed a prototype machine that we didn't really understand exactly what it was going to cost us to build. So he built into the job some interesting incentives that if we met certain project construction points along the tunnel by certain dates, we would earn bonuses. But it was so bad in the early stages that I was really almost betting the entire company that we would succeed. So it was a big risk for a small company like ours.
But it isn't just contractors like the Robbins Company who are gambling their future. Because the entire project is privately funded, Eurotunnel officials must hit their own deadlines to continue to receive funding. With each new delay, the entire fate of the Eurotunnel lies in the balance.
The one thing we all understood was that if we stopped, it would be very hard to restart. The relationship with the banks, the problems with the contractors, the difficulties with the governments, or just plain organizational difficulties of whatever kind, would very probably bring an end to the project.
Finally, engineers are able to redesign the mechanical flaws in the French TBM and move ahead.
but they are now 9 months behind schedule. To make up the time, both the British team and the French team must stay on course. But how will these mole-like machines, tunneling towards each other from opposite directions, maintain such a specific course? They are far too deep below the Earth for high-tech satellite mapping to be of any use. And even the slightest deviation in their course, a fraction of 1 degree, will mean they fail to meet up under the channel. To remain on track, tunnel engineers use a space-age laser beam guidance system. Here, a red laser emits a beam from behind the cutting head. As it sends a beam of light forward, it hits various control points fixed to the tunnel wall before striking a special target on the rear of the cutting head. These control points feed information provided from the laser straight into the machine's onboard computer. From the TBM control cabin, operators can now adjust the hydraulic rams that thrust the TBM forward and keep it precisely on the right course. But even if the two machines do stay on course, the complex plan for after they meet has never been tried before. As the French and British TBMs tunnel towards each other, they will reach a designated point where they will stop. They will now be a mere 100 yards apart. At that point, a long steel probe will be sent through to determine if they have been truly on course. If so, more conventional equipment will finish the relatively short distance that remains. But if the two machines are off course, it will mean yet another delay while engineers try and come up with a solution. And with the project's skyrocketing budget under fire, more delays could signal the end of the dream called Eurotunnel. (1989). The year begins on a positive note at the Eurotunnel construction sites. The earlier problems with the French tunnel boring machines seem to be solved. One of the giant TBMs even sets a world tunneling record. For almost 3 years, work on the tunnel has progressed without a fatality. But in the first days of a new year, a time usually associated with hope and new beginnings, tragedy lies just around the corner. On January 20th, in the dark recesses of this massive cavern, the tunnel claims its first victim. 19-year-old engineer's assistant Andrew McKenna is walking half a mile down the tunnel beside the narrow-gauge railway tracks used by the supply carts. Apparently failing to hear an oncoming train, he is suddenly crushed to death by a locomotive carrying spoil from the site. Without warning, the stark reality of their dangerous jobs becomes clear to every worker. The tunnel has claimed one of their own. Even with 20th century technology, the job of building tunnels remains extremely hazardous. While workers cope with the loss, they also have to deal with other day-to-day fears brought on by the tunnel.
At the pumping stations, they actually went underneath the tunnels, and they would be like a little tunnel under the main tunnels. So the trains would be going above you, and you could be down working in 3 foot of water in a little cross passage with a blank wall with nowhere else to go. And that could be very claustrophobic, and we actually experienced people being sent in to work with us who were and found out they're claustrophobic. And then it became a little bit scary because you had to say to them, look, you can't work with us down there, you're terrified of the situation. And you had to think of everybody else's safety. It was dark, it could be dusty. So you had to be able to cope and have a sort of positive outlook, really.
Even with the most rigid of safety standards, the death of Andrew McKenna will not be the last tunnel casualty. In all, 12 people will die in this historic and sometimes tragic undertaking. And while the mood of the workers has turned suddenly dark, the tunnel itself remains unchanged. Here, it is always dark. Workers who refer to their machines as moles are left wondering if they are the real underground creatures.
You could be on a day shift where you arrived at work 5 o'clock in the morning and it was pitch black. You could go into a tunnel, work all day in darkness or semi-light, not bright, and then you come out at 5 o'clock at the end of your day and it was dark again. So you could go a whole week without seeing daylight. And that was a very weird experience because, you know, it's daytime and yet you never saw it.
As workers move forward in the darkness below ground, above them, work continues on the high-tech trains that will use the system when it's finished. The new service being created exclusively for the Eurotunnel is called Le Shuttle. Tunnel officials say the name is an example of the Anglo-French cooperation that characterizes the project. When finished, Le Shuttle trains will carry passengers in their cars on a continuous loop between the Folkestone terminal in England and the Calais terminal in France. In plants like these, workers use more than 10,000 welds to mold more than 5,000 parts into the single shell of a train car. Each Le Shuttle train is being specially built for the frequent trips and heavy loads it will haul. To provide maximum power, a 132-ton locomotive is placed at each end of the train.
They have to be very special trains because the trains themselves are half a mile long and they have a lot of cars inside them or a lot of trucks, and therefore the locomotives have to be very powerful. They're the most powerful locomotives in the world.
Each of these locomotives must be capable of pulling a 2,400-ton train by itself. For this kind of power, they will draw upon 25,000-volt electrical cables. This high-voltage energy source provides the equivalent force of a 7,600-horsepower engine, about 100 times the power of an average car. While the shuttle trains have the most powerful locomotives on Earth, the sleek Eurostar trains have the world's fastest. The Eurostar passenger line uses the popular TGV trains, which will travel from Paris to London at speeds of 185 miles per hour. While in the tunnel, the trains will travel at more subdued speeds, approaching 100 miles per hour. Because the transporting of commercial freight will be so important to Eurotunnel's economic success, huge new rail cars are designed to transport heavy trucks. Each freight shuttle, also a service of Le Shuttle, will have 28 carrier wagons like these. Each carrier wagon can accommodate a truck weighing up to 44 tons. Below the earth, there is no finished railway for any train to travel upon. But that is about to change. It is now October 30th, 1990. There is a new feeling in the air today, a feeling of expectation. After 3 years of tunneling, the British and French TBMs digging the service tunnel, which will run between the two rail tunnels, have arrived at their undersea destination. Facing each other under the English Channel, 100 yards apart, the machines have stopped their digging. It is strangely quiet. The same question races through each worker's mind. Have they lined up? A probe is sent through. There's a tense silence. Each worker at every level of the project knows it will be a catastrophe if the tunnels are off course. This would be the type of mistake that could fuel the flames of anti-tunnel sentiment into a raging fire. Finally, they get the news. The tunnels line up. England, by virtue of a 100-yard pole, is no longer an island. After boring through 23 miles of solid rock, the tunnels are only off by 20 inches, well within the acceptable safety margin. It is a momentous achievement. While the project's workers, a unique collection of specialists from across the globe, revel in their victory, a celebration is quickly planned for the face-to-face breakthrough. Since there is still a 100-yard gap between England and France to close, it is decided that the official breakthrough of the service tunnel will take place on December 1st. As workers return to their jobs with a new sense of accomplishment, a lottery is held to pick one worker from each country to meet in the completed tunnel. Meanwhile, there is the problem of what to do about the last 100 yards. It is too expensive to retrieve both the French and the British machines, so a unique solution is developed. The British aim their machine downward and effectively commit mechanical suicide, burying the high-tech behemoth deep into the earth. This allows the French TBM to move forward and connect with the British side of the tunnel. December 1st, 1990. Finally, the moment of truth arrives. A thin layer of chalk, essentially a prop for this massive media event, is now all that separates Frenchman Philippe Cosette and Englishman Graham Fagg. With a couple of well-directed jackhammer blasts, a barrier that has stood for 10,000 years is gone.
They're through. Hey! There's the handshake we've all been waiting for, Mr. Fagg and Mr. Cosette.
One of the most ambitious engineering efforts of the 20th century climaxes with a simple gesture of goodwill. Hundreds of feet below the English Channel, a Frenchman and an Englishman meet through a small hole. For the first time since glaciers ripped them apart thousands of years ago, France and England are once again linked.
The atmosphere was absolutely electric down there. Not only just at the breakthrough, but afterwards. And people were moving. We all felt European. I don't think anybody felt English or French. We were all European at the instant and for the brief hour before we could actually set off back to our respective sides. Amazing scene. Really wouldn't have missed it for anything.
The next few months will hold many more extraordinary moments. The public gets their chance to share in history with the above-ground breakthroughs. First in France, and then in England.
When that tunnel broke through, there was a party that would end all parties. It practically went all night. It was at the Windsor Castle on the British side. Fireworks and feasting and about 1,000 guests, and it was really a marvelous party.
What I remember is sitting down there, having the feeling there is no more machinery running now, and a feeling in amongst the most tremendous uproar, popping champagne corks and backslapping and cheering and so on, a feeling of absolute silence. It was the most extraordinary feeling.
But amidst the revelry and the silence, the realization begins to sink in that there is still a long way to go. 2 more tunnels need to be created, not to mention the installation of the high-speed railway. Work on the Eurotunnel is far from over. As the parties celebrating the breakthrough of the service tunnel fade away, efforts to complete the 2 remaining tunnels resume at an energetic pace. The 2 main rail tunnels are called running tunnels. To allow trains to switch from one track to another, massive crossover caverns are carved from the seabed. 40 feet high and over 500 feet long, they are the largest undersea caverns ever created. Workers refer to these massive structures as cathedrals, but in the event of a deadly fire, they could quickly become a scene of mass terror. To prevent fire from spreading from one running tunnel to the other, engineers build giant doors to separate the 2 tunnels. Each door is made from super strong carbon manganese steel. Then, a half-inch layer of flame-resistant material is added. These fireproof walls are a movable fortress, weighing over 100 tons each. But fire isn't the only emergency tunnel officials must prepare for. terrorist attacks, bomb threats, and even the remote possibility of an earthquake are all scenarios which must be planned for.
The evacuation train will be with us in approximately 6 minutes' time.
Specially trained security force and evacuation teams are established that constantly rehearse emergency procedures. While they speak the same language in times of emergency, French and British officials still have different beliefs regarding issues of safety.
There are two different safety philosophies. The French have a belief in intelligent operators using sophisticated equipment, but in charge of the equipment. The British have a culture of fail-safe computers. Channel Tunnel, you've got an aggregation of both, so you can be quite sure whichever you think is better, the tunnel's got it.
No other tunnel in the world is as safe as this one, with the central service tunnel, the fire supply systems, duplication of power supplies, emergency walkways, and all the procedures that have been put in place to cover every eventuality.
But there is one eventuality engineers haven't planned for. As engineers perform test runs in the tunnels, the friction of the trains is producing an enormous amount of heat, raising temperatures to a scorching 140 degrees Fahrenheit. Scrambling for a solution, engineers create a pipeline filled with chilled, flowing water to keep the heat in the tunnel from accumulating. This cold water acts like a sponge to absorb the tunnel's heat. The water, now very warm, is then pumped to a cooling station on shore, re-chilled, and recirculated once again. Elsewhere, the two stations that will serve as Eurotunnel's passenger hubs are beginning to take shape. The massive French terminal at Calais is one of the largest construction projects in the world. Within its sprawling 11-mile perimeter, the Calais station will have 30 miles of roadway and 30 miles of railway track. While the British terminal at Folkestone is tiny in comparison, 5 times smaller than the French station, it will house the nerve center of the entire Eurotunnel system.
Cross passage door 5650. You're across the opening. Stand by, please.
Here in the Folkestone Command Center, operators use state-of-the-art technology to control all of the rail traffic that moves through the tunnel. Sitting behind 3 rows of desks, they can survey a curved wall showing the status of the entire system. This high-tech display is called a mimic board. It shows the position of every train in the tunnel and at the terminals.
Door clear, opening now.
In the event of a power failure, tunnel control will immediately switch over to the Calais Control Center, which is staffed at all times in case of emergency. Even the drivers of the shuttle trains will receive a little high-tech help. In this driving simulator, operators practice navigating through the tunnel. In real life, the driver of each shuttle will sit in the front locomotive, while the captain of the train sits in the rear locomotive. The captain, who is ultimately responsible for the safety of the passengers, communicates with the driver by intercom. But the onboard computers also have command status. If the train begins to move too fast, the shuttle brakes will go on automatically. By the middle of 1991, the project's infrastructure is beginning to take form. From the terminals to the trains themselves, it is beginning to look like the dream of an undersea rail link will be realized. But deep underground, 2 more hurdles remain. The completion of the northern and southern rail tunnels. On May 22nd, the first of those obstacles disappears into history as the Northern Running Tunnel is finished. This is the tunnel that will carry passengers from Britain to France, but today it is a symbol of a united Europe. Just over a month later, on June 28, 1991, more celebrations as a huge crowd gathers for the completion of the Southern Tunnel. The last TBM punches through the remaining wall and comes to a stop. 4 years after the digging began, one of the most difficult engineering challenges in history is now complete. While workers celebrate and drink champagne, the machines finally fall silent. In the long, colorful history of these 2 countries, this is a singular moment. French or British, project chairman or supply cart driver, for a moment, it doesn't matter.
What is being created here and what has been achieved to date is of enormous value for the future of both our countries and of Europe. Thank you.
In all, over 13,000 workers have labored for more than 6 years. Besides the 3 main undersea tunnels, each over 30 miles long, 9 other smaller access tunnels were also created. The amount of material removed on the British side increased Her Majesty's kingdom by 75 acres. Engineers believe the hard part is over. In fact, contractors like Richard Robbins collect bonuses for finishing ahead of schedule. But when today's party is over, tomorrow morning will usher in the stark reality of a bloated budget and an uncertain future. To Eurotunnel officials, the hard part may have just begun. With the digging of the Southern Railway Tunnel finished, the 7-year struggle to build the world's longest undersea tunnel nears completion. The narrow-gauge railway tracks which carried supplies into the tunnels are replaced by a new concrete floor. This will support the wider, standard-gauge railway tracks on which high-speed trains will travel at 100 miles per hour. Over 300,000 rubber shock absorbers are installed to secure 60 miles of track. The powerful locomotives that will pull trains half a mile long 20 times a day are delivered to the terminal at Calais, France. Finally, on May 6, 1994, the grand experiment is about to begin. After boarding one of the luxury Eurostar trains in London, Her Majesty Queen Elizabeth II arrives in Calais, France. This will be just the first part of an all-day celebration scheduled in both countries. Her Majesty is received by French President François Mitterrand. After a ribbon-cutting ceremony, the Queen and the French President depart in Her Majesty's Rolls-Royce to travel on the shuttle back to England. The image is a powerful one. Not only are the former adversaries the Eurotunnel's ceremonial first passengers, they are also the public image of the new European, able to cross a once formidable barrier with grace and ease. Arriving back in England for the second phase of the ceremony, Her Majesty takes time to greet each crew member honored with making this historic inaugural journey. But as the ceremonies and the media attention fade away, so does the public's interest. Initial usage of the tunnel is far below expectations. Critics of the Eurotunnel's cost, now almost $21 billion, are again on the warpath. Less than 2 years later, evening broadcasts spread the news officials feared the most. An accident has happened in the tunnel. On November 18, 1996, fire rips through a freight train bound for England, 11 miles from the French entrance. Trapped in smothering fumes for nearly half an hour, passengers ignore requests to wait for help and abandon the train, groping their way to safety in the service tunnel. The fire is so hot, it transforms the cargo of mammoth trucks into unrecognizable lumps of melted steel. 8 of the 34 crew members suffer smoke inhalation, and the tunnel is badly damaged. What has been called the safest tunnel in the world is now brought to its knees. Amid a firestorm of public controversy, the Eurotunnel is closed. 1,500 feet of railroad track and 150 feet of the tunnel's concrete lining are wrecked and need to be replaced. The damage caused by this accident, estimated at almost $100 million, makes it one of the costliest rail accidents in history. While no one was seriously injured, public confidence in the tunnel plummets. Eurotunnel officials go on the defensive.
12 hours later, nobody was in hospital. Yet there'd been a 1,500 degrees centigrade fire 300 feet away from them. Nobody was in hospital. Now say that about a highway crash, or about a ferry sinking, or about a plane crash. You can't.
17 days later, Eurotunnel officials stage an emergency evacuation exercise designed to reassure the public the tunnel is safe. A drill critics say has more to do with public relations than public safety. Despite this disaster, the northern tunnel reopens to passenger traffic several weeks later. But the badly burned section of the southern rail tunnel is closed for 6 months while the damaged tracks are repaired. Finally, commercial freight traffic resumes on June 15th, almost 7 months after the accident. As this disaster fades from the headlines, memories of the accident slowly fade with it. But what hasn't gone away is the sacrifice made by over 13,000 men and women who created this architectural marvel. This plaque at England's Shakespeare Cliff pays tribute to the 12 workers who lost their lives working to create the Eurotunnel. Theirs was the ultimate sacrifice. But thousands of workers also gave a great portion of their lives to work far below the earth, cut off from their families and the rest of the world.
My son was 1 when I started on it, and when I finished he was 6. Now I do feel I missed a major part of his growing up by being on the tunnel.
The job of being a tunneler, of staring at a mountain or ocean and seeing a way to cross it, has always required a special type of person. A person who can exist without natural light. In suffocating holes, working for long periods of time towards a seemingly impossible goal.
Tunnelers are a special breed of people. They move around the world building holes in the ground. Most of their work is never seen by anybody else, but they do take a pride in building a good tunnel.
It remains to be seen whether or not the Eurotunnel will be a financial success. But officials say immediate financial return was not the sole concern of every investor.
The philosophy of the investors was not, curiously, mostly financial. They said it doesn't matter whether we don't see any return. We think the benefits for our children, our grandchildren, are going to be extremely important.
The Folkestone Terminal in England and the Calais Terminal in France are now ports of call to thousands of travelers. This undersea journey, for centuries the subject of scorn and ridicule, now seems routine, the shortest distance between 2 points.
If you were British and you lived here, we're an island, and if you want to get off this island, in the past, the only way is either to get on a boat or to fly. And for the first time ever now, you can take a train. You don't have to change, you don't have to get off. You get on the train in central London, and you get off, and you're suddenly in central Paris, and it's a whole new culture.
Whatever brings these travelers to England or France, the size of the world they lived in before the Eurotunnel is smaller now. A physical barrier that has stood for 10,000 years is gone. Europe is already more united.
Whatever the political structures, whatever the legislative structures, the economic and social coming together is unstoppable. And it's happening, and the tunnel plays a key part in that, and is symbolic of it.
The Eurotunnel remains one of the greatest engineering achievements of this century. For the thousands of men and women who built this tunnel, it stands as a monument to their belief that the impossible is simply a challenge, a temporary obstacle that can be overcome with technology, skill, and perseverance.
Having lived with it for the last 10, 12 years, I feel something special about it every time I come in. I'm quite amazed by the amount of work that went into the tunnel, the complexity of all the equipment, and the short time that it took to build this modern wonder of the world.
In the end, the Eurotunnel may be viewed as more of a bridge than a tunnel. As these high-tech trains speed beneath the ocean, crossing cultural barriers as they go, the free exchange of new ideas they carry with them will remain their most precious passenger.